thank you for that kind introduction. And thank you also to our hosts for organizing the World AI Conference and this meeting, an opportunity for scientists from all over the world to come together and share ideas. I'm going to talk today about a problem that I've been interested in for a while now. When we think of machine learning, we often think about problem of learning some function, really. For example, a prototypical machine learning problem, we might have a set of images, photographs, and we want to, some of them contain our mother, some of them do not contain our mother, and so a typical machine learning problem would be given a set of labeled data, images that are labeled yes or no, do these contain our mother? Then we want an algorithm that will, given those training examples, learn a function that maps from new images to yes or no, indicating whether our mother is in those new images. So it's a function approximation problem. It lies at the heart of machine learning. Now the problem I'm interested in is, what if we don't have those labeled examples? Or what if we only have a few labeled examples and then many other unlabeled examples? What if we have 10 images that are labeled yes or no, my mother's in that image, and then we have 1 million unlabeled images of faces? Is there a way, my question for today, is there a way to use that unlabeled data, despite the fact that we don't know whether it's a yes or a no image, to improve the accuracy of the function that we're trying to learn, the yes, no, my mother is there function? And there are a number of techniques of doing this in machine learning. One is to train, for example, a neural network to be an autoencoder. That is, we take the unlabeled image, we make it an input to the network, and then in the output, instead of asking the output to be yes or no, we ask the output to be the same set of pixels that we input to the network. So that kind of idea of training a neural network to produce the image again at the output, even though it has to go through a lower dimensional bottleneck in the middle of the network, is one technique that is commonly used for using unlabeled data to learn a less noisy representation of the input image, which might have pixel noise. But, and those are good techniques for using unlabeled data. But the context in which I'm interested in this problem is a little different, so let me introduce it. And I'll introduce it by telling you about a research project we call our never-ending language learner. We call it NEL for short. And these are some of the people who are part of the research team who've been developing this system. And the idea of NEL is simple. We want to build a computer program that runs 24 hours a day, forever, and each day it has two things to do. One is it has to extract facts from the internet, from the web, from the unstructured text on the web, into a knowledge base. These facts might be things like water is a beverage, or Bill Gates founded Microsoft, or roses express the emotion love. So these are belief triples, and the idea is the system should learn over time to read the web and extract these beliefs. So that's why each day has two tasks. One is to extract more of those facts than the text out there on the web. And the second is to learn to do that better than the day before. And of course, we can tell if it does it better than the day before by simply asking, if we give it the same text today that it looked at yesterday, will it be able to extract more facts correctly than it did yesterday? So that's the system we're trying to build. To initialize the system, We give it an initial ontology that defines hundreds of categories of things we're interested in, like beverages, emotions, plants, people, cities, and so forth. And also hundreds of relations between them, like person, founded company, or beverage is made from fruit. So we give it those, we give it a dozen labeled examples, but mostly we give it the web, which is a huge unlabeled set of data. So that's the problem. And so you can see this is fundamentally a problem of learning from mostly unlabeled data, because of course nobody has labeled the web to tell us what those words mean. So that's the problem I'm interested in. I want to talk about some of the specific algorithms and lessons we've learned from this, but let me begin by just giving you a quick summary of the NEL project. We started this project in January 2010. The system did run 24 hours a day until September of last year. It built up a knowledge base with about 120 million of those beliefs, like Bill Gates founded Microsoft. It learned to improve its reading ability year over year, and its reasoning ability, and its learning ability. And it extended the initial ontology that we gave it, those categories and relations, by making up new relations of its own. And all this from primarily unlabeled data, plus those 10 or 15 labeled examples we gave for each category and each relation. If you look over time at the knowledge that it built up, it built a knowledge graph. Here's a very small piece of the 120 million edge knowledge graph that it built, and you can see that it has each of these red arrows represents a belief. For example, Maple Leaf's hometown is Toronto, and Toronto's in the country Canada, and so forth. So that's a sample of the kinds of beliefs it learned to extract into its knowledge graph. And here's a plot showing over time how the system grew year by year, starting in 2010. And you can see the knowledge base, in fact, did grow significantly, up to over 100 million beliefs. And the skill level of the reading algorithms, that is the accuracy, also grew over time. So here's a plot that basically shows, yes, the system did manage to learn from this unlabeled web data over a multi-year period of time. So if you look inside, we think of this NEL system as an agent. From a more fundamental point of view, the machine learning question that I think is very interesting is, what initial structure should we give to this agent now that would allow it to learn from all this unlabeled data? And we took a very different approach from that autoencoder idea that I mentioned at the beginning. Let me tell you what we did. I'm going to use the notation, by the way, that black arrows indicate functions that are being learned. And so if you ask me what's the most important lesson from this research project, the most important lesson was it's very difficult to use unlabeled data to learn a single function. For example, one of the things NEL needs to learn is, given a noun phrase like microphone or Bill Gates or Shanghai, figure out yes or no, is this a person? It's very difficult to use unlabeled data to learn that function. But it's much easier, it turns out, to learn many functions simultaneously if you have unlabeled data. And so, in fact, in NEL, each of these black arrows represents a different function that, for any given noun phrase, some of those functions have to predict whether the noun phrase is a person, different ones have to predict whether it's an athlete. Some of those functions use the letters in the noun phrase to represent the noun phrase. Some of them instead use words around the noun phrase. And the key lesson of this talk is that if you want to learn from unlabeled data, then if you have an agent that must learn many different functions, but you know something about the relationship among those functions, then that's a much easier, you'll be much more successful having your system learn from unlabeled data in that second seemingly complex case, whereas the seemingly simple case is a much, much more difficult problem. So let's look at the algorithms and you'll see what I mean. The key idea here is that unlabeled data is very difficult to use if you're learning a single function, but even if you have two functions you're learning that are related in a particular way, already unlabeled data becomes useful. So let me illustrate. So suppose here we have one function, that one black arrow. In this function we're trying to learn, it's not classifying images according to whether this is your mother, it's classifying noun phrases that we find on the web, like Baistriki or Beijing. And it has to say yes or no, this noun phrase refers to a person. So if we input Beijing, we want to say no, that does not refer to a person. And so here would be the typical supervised training setup. We want to learn that function. It has some parameters, theta 1. Maybe this function could be, say, a logistic function. We use logistic regression. Or it could be a neural network. And theta 1 is the set of parameters of that neural network. It doesn't actually matter. What I have to say will cover both of those cases and others. But the key thing is, when we define our supervised learning algorithm, basically the problem is to choose the values of the parameters of theta 1 of the function. And the prototypical way we do that is to have the learning algorithm choose values of theta 1 that minimize the function shown here. That is, we want to minimize the sum over the xy labeled pairs that we have of how often our function f1 predicts a value for y which is different from the labeled value that's given. So it's typical supervised learning. Now, suppose instead that we have a second function that we also want to learn. This function is given the same noun phrase, and it has to predict the same thing. But instead of, but it represents the noun phrase in a different way. In fact, the red function, f1, is going to represent each noun phrase by a long vector showing how frequently on the web that noun phrase occurs with different phrases. Let's take a particular noun phrase like Beijing. So we'd ask, we'd represent it by how often does Beijing occur in the phrase Beijing is a friend, or rang the Beijing, or Beijing walked in. And you can see that if it's a person, we'll have a different distribution of frequencies than if it's a city. And suppose this blue function has to also predict whether something's a person. But instead of representing the noun phrase by its context, by the surrounding words, it represents the noun phrase by the letters. If it's Beijing, is that a capitalized word? Yes. Does it end with SKI? No. Does it contain UNIV period? No. So the second function is looking at the same noun phrase, but using a different view. Okay, now think how you could train the parameters of both of these functions, f1 and f2. And what you see is that now the objective that we're trying to optimize when we train these two functions has the same term. The first term here is the same as the previous slide. We want to minimize the number of mistakes over the label data for f1. The second term says we want to minimize the number of mistakes over the label data for f2. The third term says we want to minimize over the unlabeled data the number of times f1 and f2 disagree on whether the label is 1 or 0. And if you think about it, it makes perfect sense, right? If F1 and F2 are correctly learned, then of course they should agree on any given unlabeled example. They should either both say, oh yes, that's a person, or oh no, that's not a person. But if they disagree, one says yes, one says no, then clearly something is wrong with at least one of those functions. And so this is where the unlabeled data comes in. Once you get this idea, this is the core idea for how Nell was organized. It was this insight. Okay? And when you think about this objective function as I have it written down, what you notice is, in the case of Nell, we had about 10 labeled examples. So those first two terms, we're summing over 10 labeled examples to figure out what we're trying to optimize. But we had how many unlabeled examples? Well, we used the 25 million most frequent noun phrases that we could find on the web. So that third term, we're summing over 25 million unlabeled noun phrases to complement the very small number of labeled examples that we have. So you can see if we can get our learning algorithm to choose the parameters theta 1 and theta 2 to minimize this, then it's going to be the unlabeled data that's doing most of the work, those 25 million unlabeled examples. Okay, so once you get this idea, you see, oh, unlabeled data can be useful as long as I have multiple functions, and I know there's some constraint about the outputs that they are outputting, and there's some constraint that I can state between the outputs the two functions are providing. In this case, the constraint is the outputs must be equal. Okay, so now it turns out this works quite well. If you ask, if I run this algorithm not to predict which noun phrases are people, but instead to predict which noun phrases refer to hotels, then here are the top phrases that the algorithm learns to consider most important when deciding whether a noun phrase refers to a hotel. Like, for example, X is the only 5-star hotel. That's a good phrase. And if you scan these, you see they make sense. What about the other function that's looking at the letters in the noun phrase? Well, that function finds that these are the most important substrings in the noun phrase. So if the noun phrase has a word that ends in TEL, like Hampton Hotel, then the TEL is a good indicator, and so forth. So this algorithm is not only theoretically interesting, but practically valuable. Okay, so now let's go back and look at the algorithm again. It turns out there's an interesting theory behind this. We were able to prove that this algorithm is successful under certain assumptions. And the theorem you see here says that if you're trying to train these two functions together, we call it co-training, then as long as those functions F1 and F2 are path learnable from noisy labeled data, path learnable essentially means, it's a theoretical construct that means given enough labeled data, you can get closer and closer to zero error. So as long as F1 and F2 are learnable from noisy labeled data, and importantly, the inputs, X1 and X2, those two descriptions of the noun phrases, are conditionally independent given the label, then we can prove that F1 and F2 are also path learnable from just unlabeled data, plus a weak initial predictor. By weak initial predictor, I mean an initial estimate of F1 and F2 that's better than chance. So one way to interpret this theorem is it's telling us if we have enough labeled data to train F1 and F2 to be just better than chance, and those two views, X1 and X2, are conditionally independent given the label, then we're going to be able to use unlabeled data to learn the function. And it's true. Furthermore, the theory shows that the situation gets better and better the more functions we couple the training of in this way. In fact, the sample complexity, the amount of labeled data that we need, and the amount of unlabeled data that we need, drops exponentially in the number of views of X. So if we go from 2 to 3 to 4 to 5 functions, the improvement goes exponentially. In NEL, in fact, we not only have this kind of scheme going on to train each of the classifiers that we need for each of the hundreds of categories that NEL is worried about. NEL is considering which noun phrases are people, which ones are cities, which ones are flowers, which ones are emotions. So we do this for each of those. But in NEL, we also know relations among those different functions. So if we have a function that's predicting whether a noun phrase refers to a person, and a different one that refers to, that predicts whether a noun phrase refers to an athlete, well, you and I know, and Nell knows because we told it, that persons are required, being a person is a necessary condition for being an athlete. In fact, athletes are a subset of a person. So that's another constraint that allows us to couple the training of the functions predicting, is this a person? And the functions predicting, is this an athlete? The constraint is no longer that they must give the same output, but that, let's see, what would be illegal here? It would be illegal for the athlete function to say for a particular noun phrase, yes, that refers to an athlete, but the person predictor to say, no, it's not a person. That wouldn't make sense. You have to be a person if you're an athlete. So you see there are legal joint assignments and illegal joint assignments. And we can use that kind of constraint between the two functions in a way that's very analogous to how we used in the previous example that these two functions had to produce equal predictions. Here we're just saying they have to be consistent predictions. So when we put this idea together with the previous one, we actually have this many black arrow functions using those different views of the noun phrases, predicting these different labels for the noun phrases. And you can see now that we have many functions. And remember that theoretical result. It said the improvement goes exponentially in the number of functions that we're coupling and coaching. So now it goes beyond that because it turns out in now we're also learning additional functions that take a pair of noun phrases and say yes or no, this pair satisfies a relation. Like if I give, I wish I was better at international sports, but I'll use an American example. If I give the pair Mickey Mantle and baseball as two noun phrases, the relation that says person plays sport should say yes, because Mickey Mantle did in fact play baseball. But the relation that says coach's team, given Mickey Mantle in baseball, should say no, because that doesn't make any sense. Mickey Mantle didn't coach baseball. So we're learning these functions too, but they have to be compatible with the types. So for example, if we have a relation like person plays sport, then the first noun phrase has to also be a person, and the second one also has to be a sport. And so these are additional coupling constraints. We have even more black arrow functions. Some of them refer to single categories, some of them refer to two-argument relations, but as you can see, we get this coupled nest of interrelated classification functions. And again, this improves even more the set of constraints and therefore the efficiency and the accuracy of the learning that we get. And all of this can be done with unlabeled data now. Because again, for any unlabeled example, we don't know what category it belongs to. And for any pair of noun phrases, we don't know which relations it satisfies. It's not labeled to tell us that. But we do know that whatever the labels are, they have to obey these kind of consistency constraints. And again, that's where the advantages coming. So that's the key idea. And in L, there are over 4,000 of these black arrow classifier functions being learned, and many, many different constraints. And so that's one key idea to come out of Nell. It's actually the most important single idea that made Nell able to learn for many years and continue to improve, despite the fact that it was mostly just using unlabeled data on the web. So that's kind of, I hope you appreciate this idea. That's kind of the key lesson from Nell about how to use unlabeled data to train a complicated collection of functions that an agent might be learning. But there was also a surprise to me and to the rest of the team that came out of this once we started pursuing it. And I want to tell you about that surprise. Let me do it this way. It turns out this insight that we just talked about, that we can use unlabeled data to train functions if we have many functions that we have to learn, and they're all coupled in some way. That same insight is useful if we ask a slightly different question, which is, how could we build an agent that could estimate its own accuracy? How accurate is the collection of functions that the agent has learned? That's one of the problems we have in Nell. We wanted it to be able to self-reflect and understand which functions it was learning accurately and which ones were inaccurate. But we didn't have enough labeled data for it to do that. But it turns out there are conditions, including the condition of Nell, where you can use unlabeled data, surprisingly, for the agent can use the unlabeled data to estimate the accuracy of its own learned functions. So let me show you that result. Let's see, I have to jump a little. Okay, here's the problem set. Suppose you have n different estimates of the same function. We'll call them f1 through fn, and they're estimates of the same function. Now, in Nell, this is exactly the situation we have because we're trying to learn a function from x to y. Let's say x might be a noun phrase, and y might be yes or no, does this noun phrase refer to a hotel? And those three different estimates of the function could be the classifiers using the different views, the context around the noun phrase, the letters in the noun phrase, etc. So suppose this is the Nell setting. We have several functions that we've learned. We wish we could estimate their accuracies from unlabeled data. Now, to see the key idea here, I need to define the notion of two functions agreeing. I'll just say the agreement rate, Aij, between function fi and function fj is just the probability that on a randomly drawn example x, the probability that they'll agree. How frequently do they agree? It's just exactly what you would think of if I asked you, what do you think agreement rate means? Now, it turns out that the rate of agreement between two functions is directly related to their accuracy, because if Aij means the probability that they agree, there are only two ways that two functions can agree. Either neither one is wrong, in which case they'll agree, or they're both wrong, in which case they will agree. So Aij, the probability that they agree, is simply the probability that neither one made a mistake, plus the probability that they both made a mistake. And if we use Ei and Ej to represent the probability of a mistake from each of them, that is their error rate, and E sub ij to represent the probability of a joint error, we don't know whether the errors are independent, then we get this simple formula that relates the errors to the agreements. So now the key here to finish this off is that if we assume these errors are independent, then N term there can be replaced, we can get rid of the E sub ij, which represents the probability of both making an error, by simply the product of their independent probabilities, Ei times Ej. And so now I have an equation where I can estimate Aij just by giving a lot of unlabeled examples to these functions and measuring their agreement rates. But I don't know Ei and Ej. But if I have 3 functions instead of 2, then I end up with 3 equations with 3 unknowns. I can measure the agreement rate between function 1 and 2, 2 and 3, 1 and 3, and now I can just solve for these error rates. And when you do that, in fact, you get quite good results. Here, this is my final slide. Here, the red bars indicate the true accuracy of different functions that now has learned for classifying noun phrases as parts of the body, or beverages, or birds, or people. And the blue bar is the estimate that Nell gets when it uses its own unlabeled data to assess the accuracy of its functions. So that's what I wanted to talk about. And I hope if you get anything out of this talk, really the key idea here is in a world where we have a lot more unlabeled data than we have labeled, it's a very interesting question, fundamental question in machine learning, to understand ways in which we can use this unlabeled data. And here we've uncovered one kind of structure that an agent can have that involves an agent that has to learn many different functions, but understand some of the constraints among those functions. And in that setting, unlabeled data can be very valuable, both for learning, but also even for self-reflecting and estimating accuracy. Thank you.